Hi everyone. So my name is Zhengxun, and first a disclaimer that this talk is on my personal capacity, should not be construed to any relevance with any entity or company. So yeah, today my talk is about the engineering perspective on zero knowledge and its optimization. And this is manual for the talk. So first I would say a cliche, the optimization is important in zero knowledge. And by the way, it was originally 35 minutes talk, but shrink to 20 minutes, so I may pretty rush. But okay, so zero knowledge. So to understand why zero knowledge proving optimization is important, we need to view zero knowledge as a computing paradigm. And what it means is, if we want to run a computer on a cluster of n+1 machines, we have two ways. One is we want to run it using the vanilla way, which we pay the n+1 multiplied by execution cost. Or we can, using zero knowledge to run, and then we can choose a prover and then verify it on another machine. And to rearrange the equation, we basically get this inequality. Only if this equation holds, zero knowledge will be computationally efficient, right? So basically, the red part is verification saving they gave us, and the blue part is the prover overheads. And so basically from this equation, it basically gives us a very simple result. The prover overheads is the key to make ZK computationally efficient, because usually when we choose zero knowledge as a solution to our problem, execution cost usually is already greater than the verification cost by definition. So then the question is, how do we optimize it? A generally correct answer for any programming problem is understanding what you are programming. But there is a key difference between zero knowledge and vanilla programming, which is in vanilla programming, the strategy is simple. We directly control the hardware, the memory access control, the memory management of VARM or any other direct hardware optimizations, which leads to the success of the machine learning is a great example of this. But in zero knowledge, in most cases at this moment, there is a proof system sitting between the application and the hardware. And that imposes new challenges and opportunities. And this talk focused on opportunities. And to understand that, we need to first understand a key point. Randomness is the key as a core of the efficiency source for any zero knowledge protocol. So, and specifically in this talk, I'm going to focus on a technique that is very prevalently used in many protocols called random linear combination. And to illustrate this point, I'm going to review two very basic building blocks of zero knowledge protocols. That's probably already very familiar, but I'm still going to review it. The first is bulletproof. Specifically, I'm going to talk about the inner product arguments that is used in the bulletproof. And specifically, the claim goes like this. We have a group, which is a cyclic group of prime order P, and we have some generator, GH, and an element as a generator in the group U. And the claim is we have a Peterson commitment to these two vectors, A and B, and we also know the dot product raising to the power of U. So this is basically the Peterson commitment, and we want to prove to the verifier we know this commitment. And then the strategy is we want to use random linear combination to fold the vector half by half to the base case so that we can get efficiency. And the strategy here, how we fold it is we get a randomness, which is R, and then we fold it to get A prime and B prime using the formula, which is kind of crossing. This is really math back construction, by the way. This is not interesting math. So I want to go very deep. It's really just construction so that people ultimately will get what we want. And so the idea is if we can build a verifiable reduction to this subproblem in the form of the P prime equals the Peterson commitment of two new vector that is half the length, and also we can prove that we have this dot product of the new vector, which is a half the length, and then we can prove the correct, and then this claim only hold if we know the original claimant. Then we can focus on solving this subproblem, because if we can solve the subproblem, automatically give us the result for the original problem, and then we're done because we are recursively solving the subproblems. And then how do we do that? Well, we can let the prover compute some elements that only if it knows both sides of the relationship, it can compute correctly, and which can be also checked independently by the verifier. And the verifier can update the new commitment and new group base on its own based on the knowledge of the agreements of the algorithm beforehand without trusting the prover. So the idea is we want to split the group base because the group base is widely known by verifier and also the prover. And then we want to, and because we split the vector, so naturally, we want to split the group. And then because also in the random linear combination, we kind of do a crossing. So the group is also crossing. And it constructed like this. But this is L and R is computed by the prover because we want something that only if the prover knows the dot product of this two vector, it can compute. So we give it some very pretty hard thing. If it doesn't know, then it cannot compute. And then the verifier would compute this equation, L to the power, so I won't read it, but this equation basically is dependent on L, R, which is computed by the prover, and also a randomness that is generated by the verifier, right? Because if it's, so the reason this formula involves a randomness generated by the verifier, if it is not using the randomness, then they cannot check whether the prover actually used the correct randomness it generates. So that if this equation holds, then the original claim is correct. This is by the math construction. And now we can just recursively prove this equation holds. By folding this, we get a very exactly same equation as the previous one. And the new commitment is this. This is a new commitment, and this is a new group base. This is Hamada's. This is a pairwise product. This is pairwise product of these two group elements, and then so this is a group element. This is a group elements of size of half of the size of the original group base, and then this is the dot product of the new vector of also half the length. So then we have this new commit. We want to then the problem has been verifiably reduced to we have a new commitment and also new dot product arguments, and then this argument, and we can recursively prove this argument is correct by doing exactly similar process. And this is, this is just from the paper, original paper, and to show that actually this is what happens, right? There is a randomness that is generated by the verifier, and then the prover uses it to fold it. And then we go to FRI, fast Reed-Solomon code interactive oracle proof. And it's pretty small, but the idea is we want to prove a polynomial of low degree with overwhelming probability. And then the idea is we want to commit to the polynomial using some like tree or some whatever. And then the key is we have nth root of unity. At this point, this is kind of serving as a Reed-Solomon encoding of this polynomial. And then we use fast Fourier transformation, right? Basically here we are splitting a polynomial to the even power and the odd power. And then again, using a very similar process, we are kind of we are folding the degree to the half of the original degree, and then we use a random linear combination to combine these two lower degree polynomial to the polynomial of half of the degree. So, and then it's exactly the same process. We want to build a verifiable reduction now, such that if proving fx is of low degree on the new root of unity, which I haven't figured out, then we can proving the original polynomial is of low degree under the original root of unity. And then we have recursively solved the problem. And it turns out that we can, because of the, this new polynomial is of degree of half, so we need a root of unity of higher power, right? Basically to the power of 2. So basically we get rid of all the this like this like omega like this lower degree thing. We only keep the power of 2 root of unity. So then how many of this root of unity is of the half of the length, right? Here is n root of unity. If we get rid of all the like power of 1, 3, and 5, we get also a root of unity of length of half. It's a very similar process, right? As we can see, but here it's not a cryptography group. It's just a root of unity. So, and then we can, using this, then we need to find the new committed relationship between the new committed value and the previous committed value, so that the verifier can independently check this relationship. And the way we can do that, we can find a relationship is through this like math like deduction, right? For example, so basically, yeah. So basically, this formula is fairly like straightforward. Like, yeah. So basically, expand this. So this is just to cancel out the term, right? For example, like you plus this, you plus the omega to the I, and then negative omega to the I. You plus them together. For the even power, then it should be it should be kept, but also you have a 2 before it, so then you divide by 2. But for the odd power, then you would cancel out. So this term is equal to the this one, right? F even the omega to the 2 to the power of I. And then this is a very similar idea. And then this is rearrangement. So this equation is rearrangement of this equation. And then this equation is basically changing, or the only thing that changed is this. So negative omega I is exactly equal to W omega to the power of n divided by 2 plus I. And the reason for that is the property of root of unity. Because you have a symmetric, like the negative omega I is literally just symmetric to exactly the same position as omega to the power of n divided by 2 plus I. But okay. So then this is a relationship that we want to prove. And then how do we check that? Check it by picking a random I in this range 0 to the power of n divided by 2 minus 1 that identifies 3 points, which is these 3 points. And then this is basically just a random checking, right? This is very commonly used in any polynomial relationship checking, but here we are checking these 3 points are collinear. So if we continue, and then if this is these points are collinear, that means the relationship holds. That means the prover folds the polynomial correctly. And then if we continue doing this roughly log to the d, which d is a degree of the original polynomial times, and the prover we can and if prover folded correctly in each of the steps, and then the original committed polynomial is indeed of low degree, it's not some degree that's fairly large like n, where n is the coding ratio. Then we end up with a base case where the polynomial becomes a constant polynomial, and then therefore I can simply request a constant as the final stage, as a proof for the final stage. And if the base case is correct, it can recursively understand everything before it. So what is the learning? Some of the basic zero-knowledge building blocks are just recursive randomized algorithm. They are just recursive randomized algorithm. And then both in IPA and Fry, we are building a verifiable recurrence relationship. In IPA, verify is keeping record of updated group base for each round, and in Fry, we are checking the random point and checking the collinearity. And in fact, many other protocols follow exactly the same idea, like batch proving and other commitment schemes. But we don't have time to cover today. And so the idea is, if we can reduce the application level problem to this, how this protocol already works, then maybe you can find some more optimized way to write the application. So this is, and I'll give you an example of why this actually matters. There's many like machine learning transformers and CN and RN, there's neural nets, right? And then they involve if we want to prove, then we need to prove a relationship. R equals A, B, C, D, all these matrix multiplications. And then instead of naively compute them in circuit, the prover can instead prove A multiplied B equals E, E multiplied C equals F, F multiplied D equals R, and then computing E and F out of circuits, right? And then implement a randomized algorithm to check the matrix multiplication is indeed correct in the circuits, and then we can reusing the randomness of the Fiat-Shamir that already the underlying protocol has already computed that it exists for free, so that we can proving this. So we have finished the proving of this large series of matrix multiplication in O(n) square time instead of in naive, maybe not O(n) to the square, but still larger than O(n) to the power of 2. So the conclusion, it's important to, if you want to write an optimized algorithm for general knowledge applications, it's important to understand lower level building blocks of the proof systems, plus some hardware optimizations that everyone already talking about. And then also it's important to think of the argument that one is proving and the possibility to derive an equivalent argument to prove that can leverage underlying randomness and thus significantly make the application more efficient. Yeah, that's the end of the talk. Thanks.
If you have any questions.
You mentioned Friedwald's algorithm. I was wondering whether you can also give us a couple of other examples where we can use the randomness from.
Yeah, so for example, if we have a different polynomial, And then, so for example, we have different commitment scheme, right? And then, for example, I'll give the simplest commitment scheme, KCG. And then if we want to batch proving, for many different polynomials, their evaluation at many different points is equal to a value. And and want to batch these polynomials together. Usually, you would do naive way is you have this KCG proof for each of them, and then you need a quotient polynomial, and then do everything. And then the pairing is costly, and also the pairing would be equal to the number of polynomials you are going to prove at some points, right? But then if you want to do the random linear combination, you can random linear combine these polynomials. And then the idea is you would only need n+1 pairing, actually. So basically, because you combine this, you request some randomness, and then you combine this to a single polynomial, and then by computing the quotient. So basically, and then computing the quotient for that, and then you can send the quotient as a proof, and then verify with the random linear combine this polynomial and check whether the quotient is correct. And if that quotient is correct, then it can also it basically can be convinced with high probability that the previous that you know the value at these different points of the polynomial. Yeah, and also I think other there's also because I think like Boolean proof in later stage of the Boolean proof, there's some optimizations also using the random linear combination.
Thank you.
All good? Anyone? Okay, thank you.